Hello everyone, Kotungwane, the Nated God here. I trust everyone is doing well. And if you're tuning here for the first time, please please like, please like, and subscribe to the channel as I'll be posting more content that you find helpful. Right? Today though, we'll be looking at a problem based on beams for engineering science N4. And the problem reads as follows. A light horizontal beam ABCDE is 8 meters long. It is supported at 2 points B and D. Point B is 1 meter from the left end and point D is 2 meters from the right end. Beam carries the following loads. Now, if you look at question A, make a neat sketch labeled diagram of the beam, right? Now, even if they had drawn the beam for you, right, I always advise students that if you're looking at a problem based on beams, always redraw the beam first so that you can label it in a way that is convenient for calculating or for doing calculations for the reactions at the supports, right? Now, for this beam in particular, once you have drawn it, it is supposed to look like this here. Right, now I've drawn the beam and shown all the points on the beam, as well as all the concentrated loads, as well as the supports or the reactions at the supports. Right, I've shown all the important information. As you see, the measurements are such that they are convenient for calculating reactions at the support, right? So always redraw the beam, or always draw the beam and write down the measurements in a way that is convenient, right? Now, they said we have a UDL. The UDL is 12 kilonewtons per meter, right? So here's our UDL. The UDL is 12 kilonewtons per meter and spans from A to a distance of 5 meters, right? Now, if you notice here, there's a point that wasn't originally mentioned, right? That point is point F. Now, this point is important to have on our beam, right? So that we'll be able to show in our shear force as well as the bending moment diagram what happens in the portion of the beam from C to where to the end of the UDL. It is very important to show what happens regarding the shear force as well as the bending moment diagram. Hence, we have the point F, or hence I've given the end of the beam a point as well, right? So the point being point F, right? Now, if you have a UDL and it's in kilonewtons per meter, right, we have to resolve the UDL to its weight. Now, how we go about doing that? We say, so in this case, the UDL is 12 kilonewtons per meter, right? So we multiply this by the span or by the distance of the UDL. The UDL is 5 meters long, so you're going to multiply that by 5 meters. Then that cancels, and 12 times 5 is equal to what? Is equal to 60. So this 60 here represents the weight of the UDL. This weight of the UDL we are going to use in calculating what? The reactions at the supports. Right. Now let's look at B. At B, they say it calculates the reactions at supports B and D, right? So for engineering science N4, regarding calculating the reactions at the supports, you always have to take moments in calculating both the reactions, right? And then we only use Newton's third law of motion to prove that our beam is in equilibrium, right? So first we're going to calculate the reaction at point B by taking moments about D. So we're going to take moments about point D, right? So we're going to take moments about point D And now we're going to look at the turning effect each of the forces that are on the beam have towards point D, since point D is where we are taking moments, right? Now if you look at the 20 kilonewtons has an anti-clockwise turning effect towards B. Reaction B has a clockwise turning effect towards D. The 30 kilonewtons has an anti-clockwise turning effect towards D. The 60 also has an anti-clockwise turning effect towards D. And the 40 kilonewtons has a clockwise turning effect towards D. So our only clockwise moments are on point B as well as the force 40 kilonewtons, right? So you have sum of clockwise moments is equal to the sum of anti-clockwise moments, right? Now we said reaction B, remember we have to multiply the force with what, with the perpendicular distance from where the force is to where we are taking moments, right? So the distance between B and D is 5 meters. So this times 5 plus the 40 times the distance between 40 and D is what? Is 2 meters. Is equal to the anti-clockwise moments, right? So you have the 20 times the perpendicular distance from 20 to D. You have 6 meters plus what? Plus the 30 times 4 plus the 60. So 60 times the perpendicular distance 3,5, right? So obviously here you will have 5RB plus 40 times 2 is 80 is equal to, now if you calculate what we have on the right, we get what? We get 450, right? So 5RB, we take 80 to the other side, so you'll have 450 minus 80. Because we're looking for RB, you divide both sides by what? By the 5. Therefore RB is equal to us. Now if you punch this in, you are going to get 74 kilonewtons, right? So we now have the reaction at support B. To get the reaction at support D, we are now going to take moments about what? About B, and look at the turning effect each of these forces have towards point B, right? Now we take moments about point B, right? Now if we look at all of these forces, right, the 20 kilonewtons has an anti-clockwise turning effect towards B. The 30 is going clockwise, the 60 going clockwise, D is going anti-clockwise, E is going clockwise as well. So the only anti-clockwise moments are due to the force 20 kilonewtons as well as the reaction at support D. Every other force has a clockwise turning effect, right? So we have the sum of clockwise moments is equal to the sum of anti-clockwise moments, right? So here you have 30 times 1 plus the 60 times 1,5 plus the 40 times 7, which is equal to the anti-clockwise moments, which are due to the force 20 kilonewtons times 1 plus the reaction at D times what? Times the 5, right? Now on the right hand side we have 5 RD plus the 20 is equal to, and then if you calculate what was on the left hand side, so this here, right, what do we get? We get 400, right? Now I want to transpose the 20, right? And then you are left with the 5 RD is equal to the 400 minus 20. And now we divide both sides by what? By 5. So if you punch this in your calculators, we get the reaction support D as being equal to what? 76 kilonewtons, right? So now to prove that our beam is in equilibrium, right, we are now going to use Newton's third law of motion, right, and say sum of forces going up is equal to the sum of forces going down, right? Forces going up, you have the reaction at B and D, so you have the 74 plus the 76, which are equal to all the forces heading downward, which you have the 20 plus the 30 plus 60 plus the 40, right? Now, when you calculate the left hand side, it should be equal to the right hand side, right? So if you calculate both, you get what? You get 150 kilonewtons, and on the right hand side you also get 150 kilonewtons. So our beam is in equilibrium, meaning there's a good chance that our reactions at the support or the magnitude thereof are correct, right? So now let's look at what we must do next. So if you look at C, it says calculate the bending moment. Now I should mention that after calculating the reactions at the support, I always advise students to do the bending moment calculations next, right? The reason for that is that when you do the bending moment calculations, right, they give an indication of where we can expect the shear force to be what? To be equal to 0, right? I'll explain once we are finished with the bending moment calculations, right? So we're going to calculate the bending moment at each of the points which I've named on my beam. So at point A, B, C, F, D, and at E, right? Now, it is good to note that if you're looking at either a simply supported beam, right, or a overhanging beam, right, the bending moment at the ends of the beam, so on the right hand end as well as on the left hand end, right, the bending moments on those points is always equal to 0, right? And the reason for that is because when doing bending moment calculations, right, you can either consider forces on the left of that point or you can consider forces on the right of that point, right? And if you look at, for instance, the left hand end of this beam, right, so point A, there are no forces on the left hand end. Hence, even if you use forces on the right of point A, right, the bending moment at A will be equal to 0. The same goes for the right hand end, which is point E, because there are no forces on the right hand or on the right side of point E, right? It means the bending moment at point E, even if you look at, or even if you consider forces on the left of point E, is going to be equal to 0, right? So let's look at our bending moments. Right, let me do this instead. Let's have our beam here again, so we will be able to refer to it. Right, so see, so as explained, the bending moment at A is going to be equal to what? Equal to 0, right? So bending moment at B. So bending moment at B, we are now going to consider forces on the left of point B, right? Why? Because there's much less forces to consider on the left of point B than there is on the right hand side, right? Now, the first force you have is the 20 kilonewtons. It's headed downward, so you take it as negative. So you have the negative 20 times the distance from the 20 to point B, which is 1, right? Plus The other force you have is based on the UDL, right? Now, we are only going to consider the portion of the UDL on the left of what? Of point B. Now, the portion of the UDL on the left of point B is only what? 1 meter long, right? So what do we say? We take the 12 kilonewton per meter, right, which is the UDL, and you multiply it by what? By the span of the UDL, right, between A and B, which is what? 1 meter. So that and that cancels, and you get what? 12 kilonewtons, right? Now the 12 kilonewtons is heading downwards. It's a weight, right? So it means it is negative, right? So you're gonna have negative 12. Now the distance, remember, the weight of the UDL always acts at half the span of the UDL, meaning what? The 12 kilonewtons, which is the weight of the UDL between A and B, right? And that weight is going to act at half of the span of the UDL between A and B. The half the span of the distance, since the distance is 1, means it's what? Means it's 0.5, right? Those are all forces to consider on the left of B. And what do we get here? We have negative 26 kilonewton meters. Right, I forgot 20 kilonewton meters here as well. Right. Now we look at the bending moment at what? At point C. Now we are still going to consider forces on the left of C, because there's much less forces to consider on the left of C than there are on the right of C, right? So the first force we have is the negative 20, right? The distance from 20 to point C is equal to what? 2 meters, right? And then we have the reaction at B, right? Remember, the reaction at B was equal to what? Was equal to 74. So we have the 74 is positive because it's headed upwards, times what? The distance between B and C, which is equal to what? 1. Plus, now again, we now have to consider the UDL, but the span of the UDL now is between A and C, and the span of the UDL between A and C is what? Is 2 meters. So we say the 12 kilonewtons per meter times what? Times the span of the UDL between A and C, which is what? 2 meters. So that and that cancels, and what are we left with? 12 times 2, which is 24 kilonewtons. 24 is the weight, meaning it is negative. Now the 24 kilonewtons is going to act at half of the span of the UDL between A and C. Now the span of the UDL between A and C is 2 meters. Half of that is 1 meter, right? So we say plus the negative 24 times what? The distance from the weight to point C, which we've established, is 1. So if you punch this in your calculators, you're going to get 10 kilonewton meters, right? And the bending moment at point, so because point F is before point D, we're going to have at point F, right? And then if you look at point F, there's much less forces to consider on the right of F than there are forces to consider on the left of F, right? So we're going to consider forces on the right of F, right? Now from the right you have the negative 40, right? So you have the minus 40 times the distance from the 40 to F, which is what? 3, plus the reaction at D, which was 76 kilonewtons, right? So 76 is positive because it's going upward, times the distance between the reaction D and F, which is 1. Now if you punch this in your calculators, we are going to get minus 44 kilonewton meters, right? Those are bending moments at point F, right? Now we're going to look at bending moments at point D. So bending moment at point D. Then again, consider forces on the right of D, because there's much less forces to consider on the left of D, right? So we have the minus 40 times the distance between E and D, which is 2 meters, right? That's the only force to consider. So that will be equal to what? Minus 80 kilonewton meters, right? And the bending moment at E, right? E is the end of the beam, which of course, as we know, the bending moment on either end of the beam is equal to 0. So we have 0 kilonewton meters. Right, and this becomes our bending moment calculations. Now, looking at our bending moment calculations, right? Below the 0 line, maximum bending takes place at what? At point D, because at point D, that's where you have negative 80 kilonewtons, which in magnitude is the most looking at, or when we look at the bending moment diagram below the 0 line, right? So looking at our calculations, we would expect the shear force diagram to be equal to 0 at point D, right? Because as mentioned, below the 0 line of the bending moment diagram, right, maximum bending is negative 80 kilonewton meters, and that is at point D, right? Now above the 0 line of the bending moment diagram, right, we have a maximum magnitude of the bending moment of what? Of 10 kilonewton meters. So we expect the shear force to be equal to 0 at what? At point C as well, right? So because the maximum bending takes place at point C above the 0 line and takes place at point D below the 0 line, we expect the shear force diagram to be equal to 0 at point C and at point D, right? Now we're going to see if that is so when we draw our shear force, right? Which is what we are going to do next, right? Now before we do that though, let's see, right? D, they say draw the shear force as well as bending moment diagram, right? Now as far as drawing a shear force, or the shear force and bending moment diagram, always redraw the beam first and show all the important points, right? And then from those points you draw vertical lines from all your important points, right? And then you draw your shear force first, right? And then below your shear force you draw your bending moment diagram, right? Right, so as mentioned, always redraw your beam showing all the important points, right? And then of course on all your points you draw vertical lines, right? And then as mentioned, you have to first draw your shear force, right? Now both the diagrams are going to have a 0 line. So our 0 line, let's say, is going to be, okay, let's say our 0 line is right there. Okay, let's try that again. So we have our 0 line right there. Right, so this will be a 0 kilonewton line. Right. Now in drawing our shear force diagram, right, we have to have a section on the right of each point. Right, we're gonna have a section on the right of each point. Right, so you're gonna have a section on the right of each point. So wherever there's a point, you're gonna have a section. So there's a point here, you're gonna have a section there as well. You're gonna have a section there as well, a section there, and a section there. Right, so when drawing your shear force diagram, always have or always place sections on the right of each point. Right, now going back to your points, if there's a UDL on the left of your points, then you are going to have a section on either side of the point. For instance, if you look at it's A, there's no UDL on the left of A, so you're going to have the one section on the right of A. Right, now if you look at point B, on the left of point B, right, we have a portion of the of the UDL, meaning you are going to have a section on either side of point B. The same with point C, there's a UDL on the left of C, so you're going to section on either side of point C. The same with point F, you're going to have a section on either side of point F. Now if you look at point D, there's no UDL on the left of D, so you're only going to have a section on the right of D, as well as in point E, you're going to have a section on the right of point E. Right, so now we're going to consider the sum of forces on the left of each section. Right, now if you look at the section at A, we're going to consider forces on the left of that section. Right, so the only force to consider is the is the negative 20 kilonewtons. Since it's headed downward, we're going to take it as negative. Right, so we have the negative 20 kilonewtons. So we have the negative 20 kilonewtons. Right, that's the only force to consider on the left of section A. So we go to the next section. Right, so we're first going to consider the section on the left of point B. Right, and then consider forces on the left of that section. Right, bearing in mind that whatever force that is added or subtracted, right, at that section, we are going to add or subtract from what? From the negative 20. So the force that you are currently at becomes your reference. Right, so our reference was 0 at point or at section A. Right, so at section B, our reference is now negative 20. Right, so we're going to say the negative 20. Right, and then the force that gets added between section A and this section, right, is 1 based on the UDL. Right, now meaning the UDL is 12 kilonewtons per meter. Multiplying that by the span of the UDL, which is 1 meter, you get 12. Right, so 12 is the weight, hence it's headed downwards. So we say the negative 20 minus that 12, and what do we get? We get minus 32. Right, and we say the minus 32, right, is maybe somewhere there. Right, and because there's a UDL between A and B, we draw a diagonal line to indicate on our shear force diagram that in this portion of the beam we have a UDL. So we draw a diagonal line from this point to our current point. Right, and our current point being what? Being minus 32 kilonewtons. Right, and then we move on to our next section, which is this one, and consider forces between our last section and our current section. Right, bearing in mind that our reference point is now what? Minus 32. So the only force that gets added or subtracted is the is the reaction at support B, which is positive 74 kilonewtons. So we say the negative 32, then we add the 74, and we get what? 42 kilonewtons. Right, so we move from here to say somewhere there, right? And here you have the 42 kilonewtons, right? Those are all forces to consider on the left of the section we just completed, right? Now we go to point C and consider forces on the left of this section, or forces between this section and this section, right? Bearing in mind that our reference is now 42 kilonewtons, right? We have a UDL. The span of the UDL between the two sections is what? Is 1 meter. So again, you take the 12 kilonewton per meter, you multiply that by 1, you get 12, right? That 12 is the weight, so it's headed downwards, hence we take it as what? As negative. So you say the 42 kilonewtons minus the 12, and you get what? You get 30. So again, between B and C, you have a UDL. So we represent that on the shear force diagram by drawing what? By drawing a diagonal line from where we were to where we currently are, right? So supposed to go all the way to this line, right? So here we have, so 42 minus the 12 gave us 30 kilonewtons, right? And now we're going to consider, the second section at point C, right? So we're going to consider forces to be added or subtracted between this section and this section, right? Bearing in mind that, again, our reference is now what? 30 kilonewtons. So the only force to be added or subtracted is the minus 30 kilonewtons. So you say the current 30 kilonewtons, right? And you subtract this 30 kilonewtons and you get what? You get 0. So our shear force moves from there to 0, right? Right. Now we move on to point F, right? At point F, we first consider this section, right? And look at forces to be added or subtracted between the current section and this section, right? The only force to be added or subtracted is what? Is one based on the beam, right? Right. Now, bearing in mind that, right, our reference is now what? Is currently 0. So whatever forces we add or subtract, we're going to add or subtract on what? On the 0 kilonewtons, right? Because we are currently sitting at 0. So 0 is our reference at this point, right? The only force to add is 1 based on the UDL, right? And what is the span of the UDL? The span of the UDL between C and F is what? Is 3 meters. So we say 12 times 3, which is negative 36. Because remember, what we get when multiplying the UDL by its span, you get the weight. The weight is headed downwards, so we take it as negative, right? So 0 minus the 36 equals what? Equals minus 36. Right, so the minus 36, let's say it's somewhere there, right? Again, between C and F, we have a UDL, so we draw a diagonal line showing that there's a UDL in this portion of the beam, right? Right, and then here we're going to have, maybe let me draw it slightly below this, right? So we have the minus 36 kilonewtons, right? Now we consider forces on the right, we go to the section on the right of F, right? And consider forces between this section and this section, right? There's no forces to add or subtract, so we leave it as it is, right? Right, now going to point D, right? Going to point D, because there's no UDL between F and D, we simply just draw a horizontal line going straight across, right, from point F to point D, right? Bearing in mind that our reference is now what? Minus 36, right? So the only force to add is what? Is the reaction at point D, which is positive 76. So if you say the negative 36 and we add the 76, we get what? We get 40, right? So 40 means the shear force moves from this point to somewhere, say there, right? And then now we go to the last section, right? Remember, our reference point is now 40 kilonewtons, right? So because there's no UDL between D and E, you simply just draw a line going straight across. And so this line is going to be right there, right? And then when we get to this point, the only force to consider is the what? Is a negative 40. So 40 minus the 40, the shear force goes back to 0, right? And here's our completed shear force diagram. Right. Always remember that your shear force starts from 0 and must always end at 0, right? So if it doesn't end at 0, it means you've done something wrong somewhere in the shear force calculations, right? Now, as mentioned when doing our bending moment calculations, right? Again, if you look at our bending moment calculations, we expected the shear force to be equal to 0 at point D as well as point C. Why? Because looking at our bending moment calculations, right? Maximum bending takes place at minus 80 kilonewtons below the 0 line and at 10 kilonewton meters above the 0 line, right? So based on our bending moment calculations, they suggest that the shear force, right? The shear force is going to be equal to 0 at point C and at point D. Now let's see if that is the case. If you look at point C, the shear force is equal to 0, and if you look at point D, the shear force is equal to 0, right? So again, you can use that as a reference to see if your shear force diagram is correct, right? Right, now let's go to our bending moment diagram, right? Bending moment diagram, we're going to have, say, a 0 line right at that point, right? So this becomes our 0 line for our bending moment diagram. So we have 0 kilonewton meters, right? Right. Now, you can refer to your bending moment calculations, right? The bending moment at A is equal to 0. The bending moment at B was equal to what? Was equal to negative 26, right? So negative 26, let's say, is at this point, right? Now, in the portion of the beam we are looking at, remember you have what? You have a UDL. So between A and B, in fact, all the way up to point F, you have a UDL, right? So the way we represent a UDL, or the way we can indicate that at this portion of the beam we have a UDL on the bending moment diagram, we draw a portion of a what? Of a parabola, right? If you're looking at, or if you're dealing with the bending moment diagram below the 0 line, so the portion of the parabola you are going to be drawing is one of this one, right? So if the graph is decreasing, you want to draw this portion of the parabola, right? If the graph is increasing, then you're going to draw this section of the parabola, right? it will make sense just now when we draw our bending moment diagram, right? Now, if you're dealing with, or if you're drawing the bending moment diagram above the zero line, where you must show that there's a UDL in this portion, right? We draw a portion of the parabola that looks like this one. So above the line, the portion will either be this one if the graph is increasing, or the portion of the parabola will be this one if the graph is increasing or decreasing, sorry, above the zero line, right? Right, so the graph is decreasing from A to B, right? So we're going to draw the following portion of the parabola, right? Because the graph is decreasing, you're going to have something that looks like that, right? You draw it freehand, right? And then bending moment at C, so this was bending moment at B, which was negative 26 kilonewton meters, right? And then bending moment at C, which is our maximum bending moment above the zero line, is equal to what? 10 kilonewtons, right? We still have a UDL in this portion of the beam, right? So what we do is you continue the parabola below the zero line. So you're going to continue drawing. You already have this portion of the parabola, right? So now you're going to continue. Because the graph is increasing, you're going to have something that looks like that below the the zero line, and then above the zero line, because remember you have to draw something that looks like that. You're going to continue drawing this and have something that looks like that, right? So what I mean is, so at point C, the bending moment is 10 kilonewtons, right? 10 kilonewtons, let's say, is at that point, right? So you're going to continue, complete your parabola at the bottom, and then above the zero line, it's going to look like something like that, right? Let's redraw this. It's going to look something like that, right? So here you have 10 kilonewton meters, right? And then you have the bending moment at F. The bending moment at F is equal to what? Negative 44, right? So let's say negative 44 is at that point, right? So remember, between C and F, you still have a UDL, right? So we complete this parabola, and then you have this section of the beam. It looks like that, right? So at this point you have the minus 44. So at this section you have the minus 44 kilonewton meters, right? There's the bending moment at F. So bending moment at D, because there's no UDL, we are going to draw a diagonal line now, right, from the current point to point D. The way we represent or the way we draw the bending moment diagram, where, or in the portion of the beam where there is no UDL, you simply just draw a diagonal line, right? So if we say that's 80 right there, you simply just draw, so you use your ruler at this point to draw a diagonal line, right? Draw a diagonal line, and that's where you have your minus 80 kilonewton meters, right? And then the bending moment at E is equal to 0. And then of course, between D and E, there's no UDL, so we are going to draw, using our rulers, a diagonal line from point D to E. So you simply just draw a diagonal line to this point, right? So you can use freehand, where you have to draw portions of a parabola, right, to represent a UDL in the portion of the beam where you have a UDL. And then in the portion or portions of the beam where you don't have a UDL, you simply just use your ruler and draw a diagonal line. right? And your bending moment diagram will look like this one here, right? Now let's see if there are any more questions here. Calculate the magnitude of the maximum bending moment and its position, right? Now, we've already established, right? Remember what I said earlier, that one of the reasons why it is important in drawing your diagrams to first draw the shear force diagram is because where the shear force diagram is equal to 0, that is where we can expect bending moment to be experiencing its most bending, right? Now, we had already established that maximum bending is going to take place at either point C or point D, depending on which of the points has the greater magnitude in terms of bending moment calculations, right? And that point is what is point C. And if you look at negative 80 and 10, right? 10 is the larger number, right? When looking at the number line. So maximum bending, we are going to say, is taking place at point C, right? And C is 2 meters from the left, so that will be the distance, right? So this is number on, this is number E, right? Calculate the magnitude of the maximum bending moment and its position, right? So for point E, let's say the bending moment max, right, is equal to what? So we said it's at point C because that's where maximum bending, or that's where we have the biggest value of the bending moment calculations, right? So the maximum bending, the value is 10 kilonewton meters, right? And the position is, so the position or distance, okay, let's say position. So position equals 2 meters from the left, right? I hope you find this video helpful, right? Like I said, if you find this video helpful, please like and subscribe, and also stay tuned for more content, right? Thank you.